Hello and welcome to the Scooby-Doo R package tutorial. So what we're going to be doing here is going through each of the download steps and then the individual functions that we have in the Scooby-Doo R package. First of all, I'm going to bring your attention to this vignette here. This is where you can find a lot more of the information about the Scooby-Doo R package and the raw R files. Just as an example here, I'm going to show you, what's this page? And what we can do is then just scroll through this and you get a little bit more of in-depth information about the individual R packages and what the code is and what they individually show. But if we come back to our R screen here, there's just a note to say that Scooby-Doo does use the JAG software, which is just another Gibbs sampler by Martin Plummer. And essentially this helps us with our MCMC model. So we can find this using either just typing in JAGs into Google or using this web link here. So just going to type this into Google. And essentially what you can do now is we can start looking at the download options. So I have a Mac, so I would be clicking on here, but in Windows here. Now, if you just click the green button, it will find the most appropriate type of download for your computer. Once that's done, first of all, we need to ensure that we have DevTools downloaded and installed, and then brought up by the library. Essentially because we are using GitHub to download the Scooby-Doo R package instead of CRAN. So once this is downloaded, and once I can library, we can then go ahead to use this link here to download the package. So it's just Laura Boyle /Scooby-Doo. So if I try to run this here, I'm going to get this error message here because I've already downloaded the package. So what I would do is just use the library function to then open up the package here. So the next part of this tutorial is talking about data upload. You can upload your own data using whatever upload source you'd like and save it as modern data, fossil data, whatever you'd like to call it. But I'm going to be using the data stored in the Scooby-Doo package. So this is modern data and fossil data. And this creates us two data sets of XRF data. So the modern data set is a modern calibration data set with our most recent period of XRF data with an overlapping climate time series. So here I use temperature in anomalies. And then we've got the rest of the overlapping XRF data. Note that the age is in oldest to youngest here. And on our BigNet page here, we explain why this is. And then if we do exactly the same for the fossil data, we've got the rest of the data that doesn't overlap with the instrumental temperature data set. And once again, our age is in age common era from the oldest to the youngest, and then the rest of the XRF data. So like I said, this is the data that is stored already within the Scooby-Doo R package. But if you're going to upload your own data, then please do make sure that it's in a similar format in terms of age going from oldest to youngest, the climate time series in the second column, and then the rest of your XRF data. So first of all, the first package or the first function is Scooby-Doo input. This essentially takes the modern data and the fossil data and sorts it to be most appropriate for the model. So we've just saved this as input. And if we go and have a look at what the structure of input is, it is basically sorted out the ages, the temperature, rescaled the data, and for the modern and for the fossil, and holds any extra information that we might need for the model. So once that's run, that should run really easily. If you do have errors, then just make sure that your table is looking something like this. And then once that is through, we can start with our Scooby-Doo cal function, which is all about calibrating data. So this takes essentially the modern period and learns about the relationship between the elements and the XRF elements and the climate time series. Here I have added true, so capital T for plot and for summary, and this will just bring out a plot and a summary for us. Okay, so what we're going to be doing then is the calibration data, which takes our SCUBIDO function and takes the input data, which we've stored up here, and this mostly has the modern calibration data, which we're interested in. And there's two optional functions here. I have said that I would like to have an output plot and I would like to have an output summary, but you can change to false if you so wish. But for this tutorial, we're going to change to true. So we're going to store this as our calibration data set, essentially. So when I run this, what we're going to do is we're going to have a count up to 100%, and this is going to have 2 bars. Depending on the different types of data or the amount of data that you have, this is going to vary in length of time. Sometimes it will take 2 minutes, sometimes a little bit longer. So once this is finished, what we get is, because we've added in a true for the summary and a true for the plot, we first of all get a summary output, and this has all the information that we need about our individual priors that some people may be interested in. And a lot of this may not be too useful for you, but what we do want to be sure is that the R hat value in this column here, all of these are less than 1.1 or 1.05, as this is essentially a indication of our convergence. So in this example, everything is approved and we could be happy that our model has fully converged. We've also added in plot up here, so what we can do is we can look at the plot. So these individual plots show the relationship between the individual elements and the XRF data. Now it's important to note that in this package and in this model, we don't just take the individual element relationship. What we do is we build all of these together to look at the covariance between these, and use these somewhat low relationships to build a larger relationships when they're all compiled together. Okay, so this is stored in calibration, so we can just plot out essentially again what this is. And then we can move on to the final package, which is SCUBIDO reconstruct. So once again, what we do is we use the previous data set, so the calibration data set which we've just stored, and we add this into here. And once again, I would like to see the graph plotted out. And I'm just going to save this to reconstruction. Now, what we do is we first of all get this warning message in orange here, and essentially this says that it's going to take probably quite a while to complete. For a data set of, say, the last 10,000 years, it wouldn't be too uncommon for this to last at least about 10 hours. For something a little bit shorter, it could last, say, a couple of hours. For this data set that's already uploaded, I think it takes about 10 minutes. But this just warns you to say that this is going to take a while for this to complete. If you're happy with this, you can just press enter or escape if you would like to cancel it. But what this is going to do is it's going to count down basically the number of rows. So for example, in this XRF data set, we have 569 rows of data. And so what it's doing is it's going row by row and applying the model, what we've learned about from the calibration, onto this final reconstruction. So this is why it's going to take a little bit of time. Okay, so we've just skipped through most of the data here, but it's still counting down and it's soon going to reach 0. Now, what this is going to do now is it's going to fit the second model, hence why we've got another progress bar here. This one might take a little bit more time than the first one that we did for the calibration data set, but please do not worry, this is all part of it. Okay, so once that's finished running, we might get a few warning messages about the plot itself. But essentially what we've done here is now converted it to years BP and produced this type of temperature reconstruction for the last 2,000 years, based on the XRF data stored from SCUBIDO. If we take it back over to this R window here, all that we have, all the reconstruction is stored within this reconstruction file. If you would like to access this, you just add in the name of the reconstruction up here, and we can either get the full model output, which looks like this. So you've got a lot about the model information, the type of iterations, and the full output. But we're interested in getting the data set, the data frame that we can save ourselves and then use and explore ourselves. So what we're going to be doing here is we're going to be storing the reconstruction data frame. So in this data frame, just going to do the first 6 rows here. We have HBP, HAD, the median temperature, and then we have all the confidence intervals calculated here for 95%, 50%, and 75%. Now, the final stage of this is essentially exploring your own. So you might want to be able to save this data set. And so what we're going to do is just simply saving it down here. Any other questions that you may have, please do drop me an email. But apart from that, this tutorial is finished, and I hope you can use Scooby-Doo to explore paleoclimate using your own records. Thank you very much.